Yeah, thank you for a nice introduction. Hello everyone, I'm Wonsup Yoon, and I represent our work, Adios, to busy waiting for microsecond-scale memory disaggregation. This is joint work with Jisu, Wonsup, Kwon from KAIST. For most of us here at EUROSYS and ASPLOS, memory disaggregation is a familiar concept. But for those who might be new to it, let me give a real brief introduction. Memory disaggregation decouples memory from traditional servers and builds separate compute and memory nodes. This way, compute nodes now have access to memory of size beyond a single server. This design promotes better memory utilization and scalability in data centers. Memory disaggregation systems usually utilize paging to offer virtual memory for transparency. In memory disaggregation systems, busy waiting is a popular technique to reduce page fault handling latency. Let me show step by step where the busy waiting takes place in page fault handling and how it reduces latency. Here on the left are the CPU and RDMA NIC or RNIC of the compute node. And on the right side, there is a memory node. During execution of an application, CPU may access remote memory. When the application accesses remote memory, the page fault occurs, and CPU pauses execution. Then page fault handler issues a page fetch request to RLIC. Once the RLIC issues an RDMA request to memory node, and until the page is fetched, CPU busy waits for the completion of page fetch request. When the request completes, the application executes resumes. CPU busy waits for the request completion and does not context switch to another application. This way, page fault handling does not involve any context switching and cause no overhead or, in this case, extra latency. What happens if the CPU has to handle multiple requests at a time? Let's assume there is a queue for arriving requests. Request number 1 arrives in the queue, and CPU serves it. A page fault takes place. The CPU pauses the execution and sends a page fetch request to memory node, as in you have seen the previous slide. While CPU busy waits of page fetching, new requests arrive in the queue. Because CPU is busy waiting, the arriving requests remain in the queue are not being processed. In other words, CPU's busy waiting blocks processing of other requests. This phenomenon is called head-of-line blocking. When the page fetch completes, the CPU returns to the normal execution. Here, we make another observation. Even though RLIC can handle multiple requests, it handles only one outstanding RDMA request at a time. In other words, the RDMA channel is underutilized. So, how much impact does the head-of-line blocking have on performance? On the left, we plot the throughput on the x-axis and the 99 percentile latency on y-axis. Around 1.3 mega RPS, the system is saturated, and tail latency starts skyrocketing. The latency breakdown at the point on the right. As you can see, the queuing delays are dominant factors for such a high tail latency. Let's see RDMA utilization. This is a load throughput plot, and the load increases, the effective throughput of system is kept around 1.6 mega RPS. And you may think this is due to network saturation. However, as you can see on the right side, RDMA utilization is only about 50%, even when the system is saturated. In other words, if we utilize the RDMA bandwidth more, we can gain more throughput from that. So how do we make it possible? We began our research by revisiting traditional scheduling approaches. Traditional systems rely on swap, and do not perform busy waiting. They use yield-based page fault handling. After issuing a page fetch request, and CPU yields to the other threads. We point out that here that yield-based page fault handling has a lot of scheduling overheads. Since the page fetching only takes only 2 microseconds, context switching within the window is challenging for traditional scheduler. Our key idea is to reduce such overhead. We build a high-performance user-level scheduler and eliminate busy waiting as well as the high scheduling overhead. The key challenge here is to combine systems in 2 different spaces, the page fault handler in the corner and user-level scheduler in the user space. Let me show how yield-based page fault handling improves performance. Like before, request arrives in the queue and it is handled in the CPU. When page fault occurs, pause execution and send page fetch request. When new requests arrive in the queue, rather than busy waiting, CPU context switches to the next request and execute it. By doing so, yield-based page fault handling eliminates busy waiting and head-of-line blocking. If another page fault occurs on the request, the page fault handler issues a new page fetch request. And as you can see, yield-based page fault handling further utilizes RDMA. Later, when the first page fetch request completes, CPU context switches back to the first request and resumes execution. So, how do we perform this nice yield-based page fault handling efficiently? We use Unikernel and co-design user-level scheduler and page fault handler. Unikernel offers single mode and one address space for both application and kernel. So, interaction between kernel and user part is a just normal function call, avoiding any expensive overheads. Also, using Unikernel, we can build a system that can use both the kernel level features and user level features at the same time. For example, paging and access to hardware information are kernel level features, and lightweight context switching and customized policy for scheduling are user level features. Due to these advantages, many systems adopt the unikernel design to make better operating systems, serverless platforms, and memory discrete systems. So there are so many reasons for the unikernel, the original paper, to win the ASPROS Influence Paper Awards in Tuesday Award ceremony. For efficient yield-based page fault handling, we devised a new thread abstraction called UniThread. It is our core data structure that supports kernel's paging and user-space context switching. It runs across all layers in OS, including application, user-level scheduler, and kernel page fault handler without any cost. So it makes the yield-based page fault handling very efficient. Also, it has the universal stack design, which combines all data structure and stacks into one. In doing so, it minimizes memory footprint. In memory disaggregation, local DRAM is a highly valuable resource, so we need to reduce its footprint as much as possible. We minimize the footprint for the UniThread by minimizing context size for that. As a result, UniThreads have much smaller memory footprint while offering faster context switching performance. In addition to UniThread, we have more features in our Adios. Here, we outline 3 main features. First, to deal with the temporary page fault imbalances, we adopt page fault-aware dispatching. Since page faults occur randomly, some workers may have more page faults than others. Our scheduler keeps track of the number of page faults per worker and assigns more requests to workers with fewer outstanding page faults. This way, we can mitigate the increase in tail latency from page fault imbalances. Second, we delegate polling to the dispatcher. Rather than workers busy waiting for packet transmission, they delegate polling to the dispatcher, and the dispatcher polls the completion of packet transmission. In doing so, the dispatcher polls for both packet reception and transmission at the same time, removing any busy waiting in workers. And third, we have an eager reclaimer running in the background, watching out for least commonly used pages. Our eager reclaimer secures free page at any moment, but even when it fails to return free page immediately, our reclaimer is free of mutex and thus quick to notify the workers. Please refer to our paper for details. With these abstractions and features, we implement Adios, an efficient yield-based page fault handling system with user-level scheduling. Our memory manager is an extension of our EUROSYS 2023 work, Disaggregation. Disaggregation is built on top of a unique kernel OSB. It has page fault handling latency of only 3 microseconds. For Adios, we modify each page fault handler to support yield-based page fault handling. On top of the memory manager, we have a memory disaggregation scheduler, or MD scheduler. It is a user-level scheduler for microsecond-scale latency and uses a single globally shared queue. It is well known that a single queue reduces tail latency by removing load imbalances across workers. Applications use unit thread abstraction. Once an application uses the unit thread abstraction, the rest are handled by the MD scheduler and the memory manager. Applications can use virtual memory cementing as before, sacrificing little compatibility for existing applications. Each core part consists of about 8,000 of C, C++, and assembly code. Let's talk about evaluation. We conduct experiments to answer these 3 questions about head-over-line blocking, RDMA utilization, and real-world applications. We compare Adios against 2 systems, a kernel-based system Hermit and a unikernel-based system Adios. Both systems use busy waiting and single queuing and first-come, first-served policy. And we use a load generator which follows Poisson process, and 100 Gbps links to connect the load generator, compute node, and memory node. For the first question, we conduct performance breakdown again. These are latency breakdown of Disaggregation and Adios. The first plot is the breakdown of Disaggregation, and the second one is for Adios. In this experiment, Adios has 10 times lower P99.9 tail latency overall. If we zoom the second plot around 30 kilocycles, we can see more details in the plot. As you can see, Adios has 37 times lower queuing delay than Disaggregation, and queuing delay is no longer dominant factor for the tail latency at 1.3 MHz throughput. Now, let's take a look at RDMA utilization. On the left, we plot throughput of both Disaggregation and Adios. Compared to Disaggregation, whose throughput is kept up at around 1.6 MHz, Adios throughput continues to grow linearly and reaches about 2.7 MHz. On the right, we plot the RDMA network utilization. With Disaggregation, the RDMA network was only 50% utilized. With Adios, on the other hand, the utilization reaches about 80%. Overall, Adios process more and better utilize the RDMA network than Disaggregation, getting close to the full network capacity. For real-world applications, we first conduct experiments with 2 key value stores, memcached and rocksdb. For memcached, we use 100% GET request workload, and for rocksdb, we use a mixed workload of 99% of GET and 1% of scan requests. In memcached, Adios kept the 99.9% latency under 40 microseconds and pushes the throughput far beyond 500 kilo RPS before the 99.9% latency shoots up. Hermit's 99.9% latency starts to shoot up way early at around the throughput of 100 kilo RPS and at the latency of above 50 microseconds. In RocksDB, we observed the same performance advantage of Adios, but this time the gap between Delos and Adios is bigger than in Memcached. In Delos, 1% of scan requests blocks processing of GAN requests. On the contrary, in Adios, if scan requests access remote memory, they yield to GAN requests. We also conduct two other experiments with the complex applications: Silo, in-memory transactional database, and FICE, vector search engine. Adios also offers better throughput and tail latency overall. Overall, Adios outperforms Delos up to 1.6 times in throughput and 11 times in 99.9 percentile latency. Okay, in this talk, we have presented Adios, an efficient yield-based page fault handling memory disaggregation system. It eliminates busy waiting and head-of-line blocking, which in turn results in higher throughput and better tail latency. Our system has kept the tail latency low while pushing the throughput far beyond Delos and Hermes. When we started this work, we coined this acronym for asynchronous disaggregation operating system. In this time of microsecond tail latency, we believe our yield-based approach is a promising direction in reducing queuing delay in I/O and communication. We plan to look further into other systems. Our paper and slides are available at the link provided. Thank you so much for listening to my presentation.